Thank you very much for the invitation. And I was not a student of Anatoly Vershik, but his works, his ideas had a strong influence on me. For instance, in the 80s, he often published short notes with no details. And I remember well how I tried to reconstruct the proofs of these notes. And later, it turned out to be extremely useful for me because it gave a rise to my some of my maybe best results, I think. So my talk is closely related to this paper by Vadim Gorin, Sergei Kerov, Anatoly Vershik, finite traces and representations of a group of infinite matrices over a finite field. So this is the group GLB. I will explain what this means. So let's fix a finite field with this number of elements. P is a prime. And let's examine the group, the general linear group over this field. These are n by n matrices, which are non-singular. This is a finite group. This is its order. And let's consider the so-called Borel subgroup, which consists of upper triangular matrices of such a type. And next, I need the symmetric group, the group of permutations of n elements, which is embedded into this group in a natural way as permutations of basis elements. And a well-known decomposition holds, which is called Breuer decomposition. The double cosets with respect to this Borel subgroup are parameterized by the symmetric group. So this is the famous Breuer decomposition. Well, so now I can introduce this main hero, the group GLB. It was invented, according to some note of Anatoly Moiseyevich, it was invented probably in a discussion in published text by Sergei Vasilyevich Kerov, Andrei Zelevinsky, and Anatoly Moiseyevich this year. And what is its definition? Let's consider matrices over our finite field of infinite order and introduce the group which will play the role of a Borel group, which consists of all matrices, invertibles, which are upper triangular. This means that below diagonals we have zeros, and on the diagonal non-zeros, and elsewhere anything. So this group, and note that this group is a pro-finite group. It is a projective limit of finite groups, because this group, these finite groups, are obtained by cutting this corner of size n by n. So this is a projective limit. And as a projective limit, it can be endowed with a natural topology in which it is a compact and totally disconnected topological group. And next, I need the infinite symmetry group, which I understand as the inductive limit, not projective, but inductive limit. This group can be viewed as the group of finitary permutation matrices of infinite order. And now, so this is a countable group. And this is, of course, a group which is non-countable and compact. Now the definition, the first version of definition. The group GLB, GL comes from general linear, and B comes because we need to emphasize a special role of this subgroup. So this group can be defined again as a disjoint union of these double cosets enumerated by finitary but infinite permutations. So what are elements of these groups? They are infinite matrices of our finite field, and any such element has a corner. One can take a corner, which is an invertible matrix, and below we have arbitrary non-zero elements on the diagonal below zeros, and here anything. Of course, this size depends on the element. One can take a larger corner, the situation will be the same, the picture will be the same. Well, so what are properties of this object GLB? I repeat that B is a subgroup, which is a profinite group, and hence a compact group. And next, our group GLB can be equipped with a unique group topology such that the group B is open. It is an open and compact subgroup. And in this topology, this group is both locally compact and totally disconnected, and in a sense, it is infinite dimensional. It's not, of course, a Lie group, infinite dimension. It's not a manifold. It is a totally disconnected object, but it is infinite dimensional, say, because it is realized by infinite size matrices. And the next remark is that one can consider the inductive limit of these finite groups, which is a countable group, and it is a subgroup of our group GLB, and it is dense, a dense subgroup. So GLB can be viewed as a topological completion of this countable group. And the next remark is that in a certain sense, this group is similar to p-adic reductive group because it is locally compact and totally disconnected. A typical example of such groups, these are p-adic groups, but it is not p-adic. What is the motivation? Let me recall that that representation theory was created by Frobenius, and he calculated, in a sense, what are irreducible representations of a symmetric group. They are parameterized by Young diagrams with n boxes. And next, James Green managed to classify all irreducible representations of general linear group of a finite field, a fantastic work, which in a certain sense it follows the approach of Frobenius, but it is much more complicated. Next, I would like to mention a beautiful book by Andrei Zelivinsky. He employed a Hopf algebra approach and emphasized an amazing parallelism between the symmetric group and GL of a finite field. On the other hand, Elmar Thoma introduced the so-called extreme characters of the infinite symmetric group, analogues of irreducible character. These are not irreducible characters, but some natural analogues of them. And it turns out that there are plenty of such objects, and they are parameterized by countably many continuous parameters. So there are plenty of them, but they admit classification. And Anatoly Moiseyevich and Sergei Vasilievich Kerov managed to find another proof of the result of Thoma, which explained the origin of these Thoma parameters. But next, it was quite natural to understand what happens with the infinite GLN, which is understood as an inductive limit. But the result was discouraging. Toma and his student Skudlarek discovered that there are very, very few extreme characters, almost nothing. And the remarkable idea of Kerov and Vershik and Zelevinsky was that the right solution is to replace the countable group GL infinity by a topological group, this group GLB, which is a topological completion. So this, it seems that, at least for some point of view, this group is a bad object, but this group is a nice object. Well, so let me only briefly mention what is the main result of the paper by Gorin, Kerov, and Vershik, which gives a detailed presentations of the ideas of the old ideas of these people. The main result is a full classification of some very natural class of unitary representations of this topological group. These are not irreducible representations, but some natural substitute of irreducible representations, the so-called factor representations with trace, one can say traceable representation, they possess characters, quite a natural sense. And it turns out that this object, this traceable representation, depend on countably many continuous parameters, essentially the same as in the work of Toma, plus some discrete parameters, also countably many. And I repeat, the continuous parameters are the same as in the context of Thomas' theorem for the S infinity. So there is a strong parallelism again on the infinite dimensional level. But now I would like to present some digression, which will explain our development of the ideas of this group. Digression is related to Kirillov's orbit method. Let me recall what is this. So assume for a moment that G is a real Lie group, not infinite dimensional, ordinary Lie group. Gothic G is its Lie algebra, and G star is the dual vector space. And there is the joint action of the group on its Lie algebra, the coadjoint action here. And G hat is the dual object of G, the set of equivalence classes of irreducible unitary representations. And Kirillov's discovery can be stated as follows. There exists some connection between irreducible unitary representations and orbits with respect to the coadjoint action. And in particular, the characters of irreducible representations should be somehow related to the Fourier transforms of orbital measures, because any orbit carries a natural measure, which is invariant. It can be even normalized in a natural way. This measure is a distribution. It is of moderate growth. One can define it Fourier transform. And it turns out that characters of representations are more or less related to this Fourier transform, which is very important result. Of course, this is true exactly only for nilpotent Lie groups and certain solvable Lie groups, but it turns out that this principle holds on a semi-heuristical level for a lot of our groups, some finite groups, even some infinite dimensional groups, p-adic groups, Lie groups, real Lie groups, groups of finite fields, and so on. This is a great principle. So now the idea now is to treat our GLB as an infinite dimensional Lie group. It is not a Lie group at all, of course. It is not infinite dimensional. It is totally disconnected, but nevertheless, one can treat it as a Lie group. So first, let's consider again the finite group GLN. It has a Lie algebra. This Lie algebra is simply the algebra as a vector space. It is the space of all matrices over our finite field. We can form the dual object, the dual vector space. It's essentially the same. It can be identified with the same Lie algebra because we have a natural duality. We have a pairing between matrices from Lie algebra and Y matrices from the dual space, forming the trace of a product. This is a pairing which allows us to identify this and this object. And now what happens for take as G our object GLB? What happens? Again, we have a natural Lie algebra. Its definition is as follows. We consider all matrices over our field with finitely many non-zero entries below the diagonal. So imagine that we have an infinite matrix, the diagonal, and anything is allowed here, and only finitely many non-zeros below the diagonal. This is a Lie algebra with respect to usual commutator. And G star, the dual vector space of our base field, is almost the same, but not exactly. These are all matrices with finitely many non-zero entries below and on the diagonal. And because of this condition, again, we can define in the same way this pairing. So this object is the dual to the Lie algebra. So, and hence we have the adjoint representation and the coadjoint representation of our group GLB on these two spaces. We only need this one. And these actions are very simple. These are simply conjugations. We have to conjugate our matrices by a group element. So we have a coadjoint action. And one can try to apply the great Kirillov's principle. Look at the orbits and take the invariant measures, try to find the Fourier transforms, and so on. But it turns out that this does not go. So what happens for the coadjoint action? First, it turns out that classifying orbits seems to be a wild problem. But what is even more important is that there are orbital measures, invariant measures on the orbit. They are well defined. But it turns out that the orbits are like the irrational winding of a torus, which means that these orbital measures are bad objects. They are not radon measure. What means radon measure? Radon measure is a measure such that the mass of any compact subset must be finite. But if you have a winding, for instance, we can immerse the real line into the torus. We can transfer the Lebesgue measure on the torus. But this is a bad object. It is not radon measure. It's impossible to treat it as a distribution, as a generalized function. It's impossible. So we have an obstacle to apply directly the Kirillov orbit method. So way out of this situation is that a reasonable substitute of orbits are ergodic radon measures. So first, we want to consider not orbits at all, but replace orbits by invariant measure and the simplest, the most elementary ones. These are ergodic. And it turns out that in this situation, all measures will be infinite ones. But nevertheless, one can say what means ergodic. As usual, ergodic means that any invariant subset either has mass 0 or its complement has measure mass 0. Well, so we have this situation, and now I would like to present some result related to this idea. These are results from 2 papers by Cesar Cuenca and myself. This is one paper, a detailed one, and the second paper is a short note with announcement of results. So I would like to explain what are results. Briefly speaking, it turns out that the ergodic radon measures for the coadjoint action of our group GLB admit a full classification. And it turns out that they depend on countably many discrete parameters and countably many continuous parameters. So there are plenty of ergodic measures, but nevertheless, they admit a full classification. This is true for the group GLB, but it turns out that GLB is not an isolated object. It should be viewed as one member of a family of infinite dimensional groups over finite fields. And so it seems to be a challenging problem to study all groups of this family. And we have at present only partial result for some other infinite dimensional groups of a finite field. So I would like to briefly, without technicality, this is not technical talk, I would like to just to present some ideas, some flavor of this problem. But first of all, what kind of mathematics is behind this problem? Turns out that the subject is related to some problems, very special problems of algebraic combinatorics. So I would like to explain some kind of reduction of problem. So I need some definition. So this is my notation for the algebra of symmetric functions. It can be defined in different ways, but let's understand it as the algebra of polynomials in countably many indeterminates, the power sum symmetric functions. And the power sums are defined as these formal expressions. They can be viewed as true functions if we assume that these coordinates decay sufficiently fast, but it's not important. And I'm sorry, I forgot to write the degree is equal to k. What this means? This means that this algebra is a graded algebra, and its grading is determined by postulating that this generator has degree k. Well, this is my notation y, my notation for a set of all Young diagram pictures like this. Next, I need to mention, just to mention, I don't want to give definition of the whole Littlewood symmetric functions. What are these objects? These are a certain deformation of the sure symmetric functions. Just as the sure symmetric functions, the whole Littlewood symmetric functions form a homogeneous basis in this algebra of symmetric functions. They depend on a parameter t. They are, in fact, a particular case of more general notion, the Macdonald symmetric functions, but I need only whole Littlewood ones. And they are indexed by lambdas, which are arbitrary Young diagram. So we have a basis, a homogeneous basis, actually a family of bases, depending on t. And the sure functions are obtained by setting t equal to 0. So this is some deformation. And let's assume for a moment that t is a positive number between 0 and 1. Now, I want to introduce some set, omega, which depends on t. It is a convex set. It is formed by linear functionals on our algebra, satisfying two conditions. First, such a functional takes value 1 on the unit element. Next, it satisfied this equation, this relation, which means that multiplying argument f by the simplest power sum functions, we have this equality. Let me call this harmonicity condition. One condition. And the second condition is a positivity condition, which means that our functional should take non-negative value on our basis. So this condition is very simple. But the combination of these two conditions defines a complicated object. This is the interaction of these two conditions which creates some interesting and highly non-trivial object. And this is a convex set. So it is a convex set. One can speak about its extreme points. So, and we are mainly interested in the extreme points. And the whole set is the convex hull of the extreme points. So extreme points are elementary objects. Actually, they are some analogs of irreducible representations. So the claim is as follows. The classification of ergodic measures, our problem, can be reduced to the description of extreme points. I forgot to write extreme points for the value of parameter t equal to the inverse to q. So this is in our interval. So we need to understand what is this. But it turns out, fortunately, that it's known. This object is known. It was introduced essentially by Kerov in a paper by Kerov. He constructed all this functional, but he could not prove that this is the whole set of ergodic, of extreme functions. And this was done much later by Konstantin Matvey. It turns out a remarkable fact is that the extreme functions are multiplicative. This happens, this is a very interesting fact which happens in various situations. So multiplicativity just means this relation. And this means that it's enough to specify the values on any set of generators, say on our power sums, and they are given by this beautiful formula, which is very similar to the Thoma formula. Here, the alphas are weakly decreasing real numbers, betas are similar, and non-negative numbers, and we have this inequality, extra inequality. So infinitely many continuous parameters. And this is the full description of this set. And using this, we can add some extra discrete parameters and understand all ergodic measures for GLB. So for this, we have to work with whole little wood symmetric functions. And what next? There are other groups. Over a finite field, there are other classical groups. So let's first restrict our attention to ordinate finite groups. So there is GLN, the most fundamental objects, the simplest one. But there are also unitary groups of even or odd dimensions. There are orthogonal groups. Again, one had to distinguish the even and odd case. And there is symplectic groups. And again, our group GLB arises as a completion of the inductive limit of these families. And inside each families, again, one can take increasing chains of groups as this parameter goes to infinity. And then one can define a topological completion in the same spirit as for GL case. Again, important key role is played by an analog of a Borel subgroup, which is an open compact subgroup and determines the topology. And so in this way, you get this certain number of families of topological and locally compact groups. And there are many, many problems. The problems similar to those studied by Gorin, Kerov, and Vershik, study representations, but also in another direction, study invariant, coadjoint invariant measures. So now I would like only briefly explain what happens in the case of unitary groups. So what means a unitary group of a finite field? There is a quadratic extension, a unique quadratic extension, just like the complex number or a quadratic extension of a real number. So one can introduce Hermitian forms, and there exists essentially a single non-degenerate up to equivalence non-degenerate Hermitian forms. So one can introduce unitary groups, a group of matrices which preserve this form. So there is no problem to define what is a unitary group of a finite field. What are our results? I think at present, because this is just the start of some project, I think the main, our result is that we managed to reduce our problem related to unitary groups in the case of related group. Again, we can reduce it to some problem of algebraic combinatorics, which is again related to whole little wood symmetric functions, but this problem turns out seems to be much more difficult, at least at present. It concerns whole little wood functions with negative parameters. But what is more important is that the kind of problems is different. There is no multiplicativity property. At least we don't see it. And the answer is unknown. But there is some indication of the direction in which one can try to go. Nevertheless, we can prove the existence of a large large family of coadjoint invariant measures, so we already know that there are plenty of measures, just as in the case of GLB, which are invariant and radon measure. They are not ergodic, but still we have some examples, I think, interesting, some special examples of ergodic measures. And of course, there is a lot of work to do with other groups, with even these unitary groups. And so this is some direction, I think, which seems to be, at least to me, seems to be interesting. Well, so I would like to stop at this moment. Thank you.
Question? Comment?
Is there any idea about extension all these things to McDonald polynomials from where they could arise?
No, I don't know. I don't know. At the moment, this theory seems to be related to the level of whole little, but I don't know. It's possible maybe that some twist of this subject can lead to McDonald polynomials, but at present I don't know.
Other questions or comments? If not, let's send Grisha what he's got.
Thank you.